Let's see how we can use the Arrhenius equation to find the activation energy for a reaction. And so let's say our reaction is the isomerization of methyl isocyanide. So on the left here we have methyl isocyanide, and it's going to turn into its isomer over here for our product. This is a first order reaction, and we have the different rate constants for this reaction at different temperatures. And let's just say we don't have anything on the right side of the line I just drew yet. Okay, so we only have the rate constants at different temperatures. And in part A, they want us to find the activation energy for the reaction in kilojoules per mole. One way to do that is to remember one form of the Arrhenius equation we talked about in the previous video, which was the natural log of the rate constant K is equal to negative EA over R, where EA is the activation energy and R is the gas constant, times 1 over the temperature, plus the natural log of A, which is the frequency factor. And this is in the form of y is equal to mx plus b, right? Y is equal to mx plus b. So if you graph the natural log of the rate constant on the y-axis and 1 over the temperature on the x-axis, you're going to get a straight line, and the slope of that straight line, m, is equal to negative EA over R. And so if you get the slope of this line, you can then solve for the activation energy. If you wanted to solve for the frequency factor, right, the y-intercept is equal to the natural log of A, which is your frequency factor. So you could solve for that if you wanted to. And so if you put the natural log of the rate constant on the y-axis, right, so up here this would be on the y-axis, and then 1 over the temperature on the x-axis, this would be your x-axis here. I went ahead and did the math just to save us some time. Right, so if you took the natural log of this rate constant here, you would get this value. And if you took 1 over this temperature, you would get this value. And so now we have some data points, right? We have x and y, and we have these different data points which we could put into the calculator to find the slope of this line. So let's do that. Let's plug those values in. So we go to stat, and we go to edit, and we hit enter twice, and then start inputting. So x, that would be 0.00213. So when x is equal to 0.00213, y is equal to negative 9.757. Let's put in our next data point. So that's when x is equal to 0.00208, and y would be equal to negative 8.903. Our third data point is when x is equal to 0.00204 and y is equal to negative 8.079. Next we have 0.002 and we have negative 7.292. And then finally, our last data point would be 0.00196, and then negative 6.536. All right, so we have everything inputted now in our calculator, and let's exit out of here, go back into stat, and go into calc. And we hit enter twice. We want a linear regression. So we hit this, and we get our linear regression. So we can see right here on the calculator, b is the slope. So that's negative 19,149. And then the y-intercept would be 30.989 here. All right, so let's go ahead and write that down. So we have from our calculator, y is equal to m was negative 19,149x, and b was 30.989. All right, we're trying to find the activation energy, so we are interested in the slope, right? So the slope is negative 19,149. And those 5 data points, I've actually graphed them down here, right? You can see that I have the natural log of the rate constant K on the y-axis, and I have 1 over the temperature here on the x-axis, and here are those 5 data points that we just inputted into the calculator. And so the slope of our line, right, the slope of this line is equal to negative 19,149. So that's what we just calculated. So to find the activation energy, right, we know that the slope m is equal to, let me change colors here to emphasize, the slope is equal to negative EA over R. So the slope, right, is negative 19,149, and that's equal to negative of the activation energy over the gas constant. And R, as we've seen in previous videos, is 8.314. So we can solve for the activation energy. So let's get out the calculator here, exit out of that, and we have, this would be 19,149 times 8.314. And so we get an activation energy of, this would be 159,205 approximately joules per mole. Our answer needs to be in kilojoules per mole. So that's approximately 159 kilojoules per mole. So let's write that down. Activation energy is equal to 159 kilojoules per mole. And so we've used all of that data that was given to us to calculate the activation energy in kilojoules per mole. In part B, they want us to find the activation energy, once again in kilojoules per mole, but this time they only want us to use the rate constants at two different temperatures, at 470 and 510 Kelvin. And so we need to use the other form of the Arrhenius equation that we talked about in the previous video. So this one was the natural log of the second rate constant K2 over the first rate constant K1 is equal to negative EA over R, once again where EA is your activation energy, times 1 over T2 minus 1 over T1. And so for our temperatures, right, 510, that would be T2, and then 470 would be T1. Let's go ahead and plug in what we know so far. So the natural log, we'd have to look up these rate constants. So we will look those up in a minute, what K1 and K2 are equal to. And that would be equal to negative of the activation energy, which is what we're trying to find, over the gas constant, which we know is 8.314. This would be times 1 over T2, when T2 was 510. So 1 over 510 minus 1 over T1, which was 470. So 1 over 470. And so now let's go and look up those values for the rate constants. So we're looking for the rate constants at two different temperatures, and our temperatures are 510 Kelvin. Let me go ahead and change colors here. So we're looking for K1 and K2 at 470 and 510. So let's go back up here to the table. Right, so 470, right, that was T1, and so this would be the value for the first rate constant, 5.79 times 10 to the negative 5. And then T2 was 510, and so this would be our second rate constant here, so 1.45 times 10 to the negative third. And so let's plug those values back into our equation. So it would be K2 over K1, so 1.45 times 10 to the negative third over 5.79 times 10 to the negative fifth. So let's plug that in. So this is the natural log of 1.45 times 10 to the negative third over 5.79 times 10 to the negative fifth. So now we just have to solve for the activation energy. So let's find the stuff on the left first. So the natural log of 1.45 times 10 to the negative third, and we're going to divide that by 5.79 times 10 to the negative fifth, and we get let's round that to 3.221. So we get 3.221 on the left side, and 3.221 on the right side, we'd have negative EA over 8.314. And let's solve for this. All right, so let's get the calculator out again, and let's do 1 divided by 510. All right, from that, we're going to subtract 1 divided by 470. So let's see what we get. We get negative, let's round that to negative 1.67 times 10 to the negative 4. So we have negative 1.67 times 10 to the negative 4. So just solve for the activation energy. Right, so we have 3.221 times 8.314, and then we need to divide that by 1.67 times 10 to the negative 4. And so we get an activation energy of 100, approximately, that would be 160 kilojoules per mole. Right? We need our answer in kilojoules per mole and not joules per mole. So we'll say approximately 160 kilojoules per mole here. So the activation energy is equal to about 160 kilojoules per mole, which is almost the same value that we got using the other form of the Arrhenius equation. Right? So the other form, we ended up with 159 kilojoules per mole. So close enough. So you can use either version of the Arrhenius equation depending on what you're given in the problem.